Right now, as you're watching this video, billions of photons, tiny particles of light, are crashing into panels on rooftops, deserts, and satellites at the speed of light. And in a fraction of a second, those invisible particles are being converted into electricity that powers hospitals, charges electric vehicles, and keeps entire cities running. But here's what most people never ask: how? Not the surface-level answer, the real answer. The quantum physics happening inside a thin slice of silicon that turns sunlight into usable power. That's exactly what we're breaking down today.
Solar energy is no longer the future, it's the present.
In 2024, solar power accounted for over 5% of global electricity generation, and that number is accelerating faster than any other energy source in history. But despite how common solar panels have become, most people, including engineers, struggle to explain exactly what's happening at the atomic level when sunlight hits silicon. Today, we're going deep. By the end of this video, you'll understand the photovoltaic effect, how a solar cell is actually engineered, why silicon was chosen over other materials, and what happens to electricity once the panel generates it. Let's get into it.
What is a solar panel, really?
A solar panel is not one single device. It's a carefully engineered system made of many individual units called photovoltaic cells, PV cells for short. The word photovoltaic comes from two roots: photo meaning light and voltaic meaning electricity. So literally, light to electricity. Each PV cell is essentially a sandwich, a very precise, engineered sandwich, made primarily of silicon. Now, why silicon? Silicon sits in group 14 of the periodic table. It has 4 electrons in its outer shell, which means it can form 4 bonds with neighboring atoms. In pure crystalline form, silicon atoms lock together in a tight lattice structure. This makes it a semiconductor, not a conductor like copper, and not an insulator like rubber. It sits in between. And that middle ground is exactly what makes it useful for converting light into electricity.
The photovoltaic effect, the physics behind it.
The core phenomenon powering every solar panel on Earth is called the photovoltaic effect, first discovered by French physicist Edmond Becquerel in 1839. Here's how it works at the atomic level. When a photon, a particle of light, strikes the silicon crystal with enough energy, it collides with an electron inside the material. That energy transfer is enough to knock the electron free from its atom. When the electron breaks free, it leaves behind what physicists call a hole, a positively charged vacancy where the electron used to be. You now have a free electron with a negative charge and a hole with a positive charge. This is called an electron-hole pair. But here's the problem. If you just leave these free electrons to move randomly, they'll quickly recombine with holes, and you get heat, not electricity. To turn this into usable current, you need to force the electrons to flow in one direction. And that's where the engineering of the solar cell becomes critical. The P-N junction, the heart of the solar cell. A solar cell is made of 2 layers of silicon that have been chemically modified in a process called doping. The top layer is doped with phosphorus, which has 5 outer electrons, 1 more than silicon needs for bonding. This extra electron is free to move. This creates what's called N-type silicon, N for negative. The bottom layer is doped with boron, which has only 3 outer electrons, 1 less than needed. This creates an abundance of holes. This is called P-type silicon, P for positive. Where these 2 layers meet is called the P-N junction. At this interface, free electrons from the N-type layer diffuse across and fill holes in the P-type layer. This creates a thin region called the depletion zone, and critically, it generates a built-in electric field pointing from the N side to the P side. This electric field is your engine. When photons knock electrons loose inside the cell, this built-in electric field acts like a one-way gate. It pushes free electrons toward the N-type layer and holes toward the P-type layer. Electrons are forced to flow in one direction. That directional flow of electrons is electric current. Now let's follow that electricity from the moment sunlight hits the panel all the way to powering a device in your home. Step 1. Sunlight hits the panel. Solar panels are positioned to maximize exposure to direct sunlight. The more photons that hit the surface, the more electron-hole pairs are generated and the more current is produced. Step 2. Photovoltaic cells produce direct current, DC. The flow of electrons through the solar cell generates direct current, DC electricity. This is the same type of electricity that flows from a battery. Current flows in one continuous direction. Step 3. Metal contacts collect the current. Thin metal grid lines printed on the front surface of each cell collect the freed electrons. A solid metal contact on the back of the cell completes the circuit. Step 4. Cells connect to form a panel. Panels form an array. Individual cells are wired together in series and parallel configurations to increase voltage and current output. A standard residential solar panel contains between 60 and 72 cells. Step 5. DC electricity travels to the inverter. The DC electricity generated flows through wiring to a device called an inverter. This is one of the most critical components of the system. Step 6. The inverter converts DC to AC. Homes, offices, and most electrical equipment run on alternating current, AC, where the direction of current flow reverses rapidly, typically 50 or 60 times per second, depending on your country. The inverter uses electronic switching circuits to convert the steady DC from the panels into the oscillating AC your appliances need. Step 7. Electricity powers your devices or feeds the grid. From the inverter, electricity flows into your home's electrical panel, ready to power anything connected to it. Any excess electricity not consumed can be stored in battery systems or exported back to the national grid, often earning the owner a credit on their electricity bill. Not all solar panels perform equally, and not all conditions are equal. Here are the key engineering factors that determine output. Sunlight intensity. More photons mean more electron-hole pairs. Peak performance occurs under direct, unobstructed sunlight, typically measured at a standard of 1,000 watts per square meter. Temperature. This surprises most people. Solar panels actually become less efficient as temperature rises. Higher temperatures increase electron movement in ways that reduce the voltage output. This is why solar panels in cooler climates can sometimes outperform panels in very hot regions, even with less sun. Angle and orientation. Panels must be tilted at the correct angle relative to the sun's path across the sky. In the northern hemisphere, panels face south. The optimal tilt angle roughly equals the latitude of the location. Shading. Even partial shading of one cell can disproportionately reduce output across the entire panel, like a weak link in a chain. Modern panels use bypass diodes to minimize this effect. Dust and dirt. A layer of dust or bird droppings can reduce efficiency by 5 to 25%. Industrial solar farms employ robotic cleaning systems for this exact reason. Cell efficiency. Standard commercial silicon panels convert 15 to 22% of incoming sunlight into electricity. Premium monocrystalline panels push toward the higher end. Laboratory cells have achieved over 40% efficiency under concentrated sunlight. The same physics happening inside a rooftop panel is also powering the International Space Station, running on 2,500 square feet of solar arrays generating 84 to 120 kilowatts. Solar farms in the Sahara, covering thousands of acres and feeding power directly into national grids. Electric vehicle charging infrastructure, solar canopies in parking lots, charging cars during the day. Disaster relief systems, portable solar kits deploying rapidly in areas where grid power has been destroyed. And on the cutting edge, researchers are developing perovskite solar cells, a next-generation material that promises higher efficiency at lower manufacturing cost than silicon. Some experimental tandem cells combining perovskite and silicon have crossed 33% efficiency, pushing close to the theoretical maximum for single-junction cells. Every time you see a solar panel, you're looking at one of the most elegant applications of quantum physics ever put into mass production. A photon, a massless particle of light, striking a slice of doped silicon, freeing an electron, and through careful engineering, that single event is scaled billions of times per second to power civilization. That is core mechanics. If this video gave you a new way of seeing something you thought you already understood, subscribe to Core Mechanics. Every week we go beyond the surface and into the real engineering and physics that shape the world. Next video, we're going deep on lithium-ion batteries, how they store energy at the atomic level, why they degrade over time, and what solid-state batteries could change about everything from your phone to electric aviation. And I want to hear from you. What surprised you most about how solar panels actually work? Drop it in the comments below.